Here we're going to talk about the mean value theorem, which is a very important theorem in calculus because it connects the average rate of change with the instantaneous rate of change. In other words, it connects the derivative with the average rate of change of a function over an interval. And so I'm going to start it with a concrete example, and then we'll formalize it in the next slide. So imagine that you drive 300 miles from New York to Boston, and it takes you 5 hours. What can we say about this situation in terms of your instantaneous velocity? Well, let's sketch a picture here. Well, first let's calculate the average velocity, and we can just do that. Well, we don't need to appeal to many formulas, but we could just say, all right, well, you drove 300 miles, and it took you 5 hours. So your average velocity was 60 miles per hour. All right, there's your average velocity. All right, so it doesn't tell you about the details of your trip, but it just tells you on average that was your speed. That was your velocity. So if you draw a picture here, we've got, you went, let's just say it was 2 o'clock right here, and you're at home. So this is time, 2 o'clock, and you haven't gone anywhere yet. And then at 7 o'clock, 5 hours later, here you are, 300 miles from home. All right, so again, this is distance. Distance, and this is time. So what we just calculated was this, as we've seen before, this is the slope of this secant line, right? Because its change, right? Its rise, its change in y is 300 miles, and the change in x is 5. So we've went 60 miles per hour. Now the claim here, and this is what the mean value theorem tells us, is that you can imagine that your distance from home is going to be a continuous function of time, right? You can't just suddenly be in one spot on your drive and then magically teleport to a different spot in an instant, right? Your distance from home is a continuous function of time. And your distance graph is also going to be differentiable. If those two things are true, then we can say for sure that at some point in your trip, you were going exactly 60 miles per hour at an instant. So there was at least one instant during your trip where you had to have gone 60 miles per hour. And it's kind of, it should allude to your understanding of averages in general. And you should think that this is not necessarily true with discrete numbers. If I have test scores, a bunch of people could get 80s, other people could get hundreds, and the average could be 90. Nobody ever got a 90, but the average was still a 90. But for this case, we're guaranteed that at one point you were driving the average speed. So what it tells us is that, and what the mean value theorem says, is that at some point on your trip, your instantaneous velocity was equal to your average velocity at least once. Could have happened more times, but at least once it happened. So if we think about it, the slope of this line here, the slope equals your 60 miles per hour. What we're basically saying is that there is some tangent, so that's a secant line, there is some tangent line that you can sketch on the interval 2 to 7 that is parallel to this to this secant line. So it looks like it might happen roughly here. So like we were just to estimate, I don't know, like 4 o'clock. At 4 o'clock, it looks like your average speed was equal, your instantaneous speed was equal to the average speed. It looks like it could happen in a different place too. It looks like right about here, maybe right at the beginning of your trip. Right at the beginning of your trip, that tangent line also looks parallel. All right, so the mean value theorem guarantees that this will happen so long as your function is continuous and differentiable. And so we'll fill in the details in the next slide, but just I wanted to use this example to give you an intuition about how the mean value theorem works in an applied context. And again, continuity is very important in this case because this is not guaranteed. You're not guaranteed to get the average in a discrete case, but in a case like this you are. So we'll formalize it in the next slide. So formally, the mean value theorem states that if y equals f of x is continuous at every point on the closed interval a to b and differentiable at every point of its interior a to b, then there is at least one point c in AB at which the derivative at that point c is equal to the average rate of change, which is given by the slope of this secant line. All right, so again, this is the derivative at a point that's guaranteed to be equal to the average rate of change over the entire interval. Okay, so analytically, that's what we mean. We mean that there exists a value c, so it's an existence theorem, really. It doesn't tell us how to find it. It just tells us that it exists. So there exists a value c such that the instantaneous rate of change at c is equal to the average rate of change over the interval. Geometrically, it tells us that the slope of the secant line on that interval a to b is equal to the slope of some tangent line. The slope of a tangent at x equals c. Alright, so again, if this function is f of x, we're stating that, let's say that's a and that's b, this would be f of a, and this would be f of b. There's my secant line, and we know that the slope is equal to change in y over change in x. And we know that there's some place where I can draw a tangent line that's parallel to that according to this theorem. So it looks like it's roughly here. So the slope of that guy would be called f prime of c. And since they're parallel, those slopes would be the same. So the mean value theorem guarantees that this would happen. Now, it's very important that the conditions, right, the hypotheses in this theorem, that your function has to be continuous on the closed interval and differentiable on the open interval, those cannot be relaxed. Those have to be in place, or else you're not guaranteed that this is going to happen. So let's take a look at why those conditions have to be met. So why must your function be continuous on the closed interval a to b? Well, because if you look at this example here, we've got a function and it's not continuous, and the average rate of change would be the slope of the line connecting P to Q, And that slope, I tried to rig it so that it's 0. But you can see that the way that this function is drawn, I decided to call the slope from p to this open circle here, this hole. I decided that that slope would be 1, and you can see that the slope of the other part. Let's just make up a slope for this guy here. That looks like it could be, I don't know, 1/2, right? So the derivative of this function, where it's defined, is either 1 or 1/2 on the interval a to b, and neither of those equals the average rate of change, which is the slope of the line PQ. So no tangent is parallel to PQ. Now it's important that it has to be continuous on the closed interval. So you also can't have a situation where your endpoints, either one of your endpoints, are open, because you have no way of linking up. You can't draw the secant line because you can't link up those endpoints. They're not defined there. All right, so it has to be continuous on the closed interval. Now it has to be differentiable on the open interval, because if you look at this graph, this function is continuous everywhere, but the average rate of change, or the slope of that secant line, is 0. And there is nowhere on this graph where the slope is 0. The closest candidate is where this corner is, or this cusp is, but a function is not differentiable at a cusp. All right. Now you can get away with it not being differentiable at endpoints, and here's an example of that case. If you just took a graph that looked like this. So let's just say these are vertical tangents right here. So the graph has vertical tangents. The mean value theorem still applies there, even though that the function is not differentiable at a or b because of the vertical tangents. So it just has to be differentiable on the open interval. So let's just finish with a quick analysis of x cubed minus 3. Does that satisfy the mean value theorem on the interval 1 to 4? That should not be a decimal point. That should be a comma. Well, we just have to check, is this continuous? Is this continuous on the closed interval 1 to 4? Now it's a polynomial, and those are continuous everywhere in their domain, so that answer would be yes. And is it differentiable on the open interval 1 to 4? And again, polynomials are differentiable everywhere, so it's going to be differentiable on this open interval as well. And so because of that, yes, this satisfies the mean value theorem, and we could apply that to that function if we had to. All right, so there's the mean value theorem. It's a very important theorem in calculus because you'll see when you do integral calculus later in the year, this is going to come up again in a different form.